Hey guys, this is a video on the basics of definite integrals. So I'm actually just talking about what the definite integral represents, kind of from a theory standpoint. I'm not like evaluating integrals. I'm just kind of going into this to make sure you kind of understand all the vocabulary because it's actually a little bit complicated. And before I get into this, to really kind of get the big picture with this, ideally, you should already feel comfortable with kind of computing Riemann sums, and even deeper, determining formulas for Riemann sums for n subintervals. So this is kind of where you use like sigma notation. You may have also already like evaluated this as n goes to infinity, so taking that limit. So this is something that's actually kind of important and is part of the foundation of this idea. Okay, so where I want to start is I want to just introduce and also review a little bit of vocabulary. So we've done this a lot with Riemann sums already. So I've got this closed interval from A to B. And kind of what we do with Riemann sums is we create subintervals. Now, what I'm going to do here is I'm actually going to create a bunch of different sizes of subintervals just to help kind of motivate a little bit of vocabulary. So technically, when you want to kind of divide up an interval, we usually do it with equal widths, but you don't have to. You technically don't have to. And so from this idea, we actually get a little bit of extra vocabulary. So first of all, I have divided the interval into, so let's count. This is 1, 2, 3, 4, 5, 6 subintervals. Okay, so subintervals is like a concept that we get. There's a little bit more, there's some other vocabulary associated with this. I just want to make sure you're aware of. So we label the kind of the different points of the subintervals. We label those with what we call grid points. So the way that we label grid points going from A to B, so A is going to be labeled as this x sub 0, and then after that, like, so this would be the most general way that you can label your grid points, right? So these are all my little grid points. So these are my grid points. Okay, now if I take the set of these grid points, this forms what's known as a partition. So for a partition, I label that P, and that's the set of your grid points. So I'll just write them out. And so I just kind of arbitrarily made this for 6. You could have this for 10 or 100. Usually the notation that you'll see is you call this n. I'm just trying to make this slightly more concrete. And okay, so from a partition, then we have what's known as a norm. So the norm looks like this. This is the notation. And this is measuring, this measures the largest subinterval width. Now, normally this would be kind of silly because I think a lot of times when you talk about doing Riemann sums, you keep your subinterval width the same. But if you did something, say, like this would be referring to then that largest width. And so from our partition, so just the last thing I guess I want to note here, so let's see, why don't I just give myself a little more space? So the partition divides, let me write this out, maybe I'll just write it out first. Okay, so the last thing is, and this is something like we kind of intuitively already know, but so you have these points P, these divide your closed interval into these subintervals. So this is how you would like refer to all of those subintervals in order. So this is just a vocabulary review just to kind of make sure you know what all the terms mean, because now we're going to actually take a look at kind of what a definite integral is, and it uses all of these terms. Now that we've got this vocabulary kind of out of the way and we kind of know some of those terms, we can discuss the mathematically rigorous definition of a definite integral. So I just want to show this to you. So let f of x be a function defined on the closed interval from a to b. We say j is the definite integral of f over this closed interval, and that j is the limit of the Riemann sums if the following is true. Given any epsilon greater than 0, there exists a corresponding delta greater than 0 such that for every partition p of the closed interval with the norm less than delta, and any choice of c sub k in one of our subintervals, we have that the Riemann sum minus the definite integral will be less than epsilon. So what the heck is this saying? So this is actually now creating a very important connection between things that we've kind of been building on. So this is saying that the definite integral is related to those Riemann sums that we were working with. And just to kind of give you a reminder, what were we actually doing with those Riemann sums? So remember, you have some closed interval from a to b, and we've talked about now, and you should kind of know, with Riemann sums, so let's pretend that if I just divided this into 4 subintervals, and I use this as an area estimate, well, I happen to know that this is really not the best area estimate, right? If I just have 4 subintervals. And even if I were to divide this like into 8 subintervals and try to make rectangles off of this, this is still not very precise. The best way that, since I can't estimate the area of this shape with a nice geometric formula, instead what I have to do is, the best estimate would be to just get an infinite amount of rectangles in this. And so that's kind of why you spend all that time trying to make those formulas for n subintervals, because the idea is, if I could take n to infinity, what does that look like? Well, basically then that's this idea that I'm just like creating so many rectangles that at some point, like, it just starts to look like I've filled in the shape because they are getting so fine. And so eventually, if I can take the number of subintervals that I have out to infinity, what's going to end up happening is I do end up getting the area of this shape. So what we've been talking about kind of with Riemann sums, we've been kind of working on getting to all of this and going through a very laborious process to figure out actually what this formula would be and taking the limit. This is kind of a lot of work. And this is now basically backing up what we've been doing so far. This concept of trying to make the width of my rectangle as small as possible, that is basically what this definition is trying to bring up. So remember, the norm has to do with the width of a subinterval. So we're talking about if you can get your subintervals down to a certain very tiny width, then at some point you actually will get to the definite integral, which ends up being the kind of the area of this shape. So that's a little bit of what this definition is kind of referring to. And this probably feels a little bit familiar to something we talked a lot more about at the beginning of the semester, the formal definition of the limit. So now when you look at the formal definition of a limit from the beginning of the semester, this probably just looks much simpler now. And maybe it even starts to make a little bit more sense. A lot of times when people learn the formal definition first, it's like this very difficult thing. And then after the course of like several weeks, it starts to sink in a little bit more. So this was really laying the foundation to get to kind of this definition here. And it's still the same idea, right? You're thinking about thresholds so that you get within a particular answer. So that's kind of like the idea. Now, a few things I do want to point out about this definition that are maybe a little bit odd. So this part here, so maybe I'll underline this. This is actually a Riemann sum, but this is kind of almost done in a strange way. If you've seen kind of other videos that I have with the Riemann sum formula, so this is kind of like a truncated, shorter version. And basically this is written so that you can have the widths of your subintervals be literally anything you want, and you can also choose any point in the subinterval. Normally when we work with Riemann sums, we're way more algorithmic about it, and we want to choose like the same point every single time, and we want to use the same width every single time. But technically you don't have to do that. And so in an effort to make the most mathematically like sound definition possible, this is kind of, we say you can choose any point you want in the subinterval, and your subintervals can be any width. That's kind of like covering the bases on that. So that's why this looks a little bit different. Okay, so now if the limit exists for our definite integral, so if we're able to kind of go through and do that whole Riemann sum calculation, and also if we use equal width partitions, which if you've been watching any of my videos, I always use equal width partitions, then instead of having that whole crazy definition that we wrote, we can instead write this. All right, so I realize there's a lot to look at. Highly recommend you actually write this down. Pause the video, write it down, and just try to figure out what parts of this actually look familiar to you. So this part here, this actually is our definite integral. So this part here, this is my definite integral. And then this part over here, so if you've been watching some of my other videos, so this is actually kind of this is the formula for a Riemann sum doing right endpoints. So this is a Riemann sum using right endpoints. So I've had quite a few videos where I've kind of shown this. So this is the definition of a Riemann sum that we're used to working with. Like I said, in the other definition, we kind of switch it around a little bit to make it like as general as possible. The formula that we use here, this is actually a little bit more algorithmic, which honestly makes it a little bit nicer to work with. Okay, so this is very exciting actually. There is now a relationship, there's like this formally stated relationship between definite integrals and these Riemann sums. And this is actually going to make our life super awesome a little bit later on, but I'm going to leave that kind of there. I do want to talk about a few things about this notation. So we have talked about this kind of in some aspects before. So this part here, so this is your integral sign. And now you'll notice that there's these a and b. So these are called your limits of integration. And that there is also the limit of integration. So f of x, this is what's known as the integrand. And then finally, let's see, I guess I'm running out of colors here, I'll use white. So this last part, this dx, so this is still your variable of integration. A lot of times when people are learning this, they tend to drop the variable of integration. It's really important that every time you do this, you always have your variable of integration, because it's basically saying what you need to integrate with respect to. If you move on to a course like Calc 3, you will have functions that have like x, y, and z in them. So the variable of integration becomes even more vital. So you want to just get in the habit of writing this out now. Most calc teachers are going to dock you if you don't have that dx there. Now, the natural question after seeing kind of this monstrosity of formula is people say, well, is this related to indefinite integrals? And so yes, it is, but that is actually another explanation that like right now we just want to understand what the definite integral is. And the definite integral, going back to this, the definite integral actually means finding kind of the area of these stranger shapes that we've been looking at so far. Now there are a few rules that come with definite integrals that I want to discuss. So we're going to let f of x and g of x just be these two integrable functions. And I highly recommend that you write these down. These are very handy little rules. We've got the order of integration, which says that if you were to flip your limits of integration, so it would equal the same thing, you just would put a minus sign in front. This next one, so this is the zero width interval. So this actually makes sense if you think about just a real quick illustration. So if I have, so here's my f of x. If you just think about going from a to a, what would the width of this particular shape be? It would be 0, so that's what that means. For the next one, we've got the constant multiple. So if you have some constant being multiplied by your function, you can just kind of bring it out in front of the integral. You are also allowed to take the sum or difference. If you have a sum of two functions, you can break these up if that's helpful to you. Or you could always go the other way too, right? So you could sum them up together or subtract them. We have additivity. So this one's actually pretty interesting. So if you have some function, so you know the value of it from a to b and then again from b to c, you can just break this out by just going from a to c. You can just go that way instead. And this makes sense again if you just kind of think about a little illustration to go with it. So if I have a graph here, here's my f of x. So if this is my a, this is my b, and this is my c, well, it would make sense why you could just instead just integrate from a to c. Then we have the min-max inequality. So if you've got a maximum value, a capital M, and a minimum value, little m, then the value of your integral is going to be somewhere between m, those values, times b minus a, so the width of your interval. Then we have the last one, which is domination. So if f of x is greater than or equal to g of x, then on some interval, then its integral will also be bigger than that. So that also makes sense. You can draw like a little diagram to go with that. And then this is something we've kind of already been seeing. So if the function is greater than 0, so if it's non-negative, then its integral will also be greater than or equal to 0. So this has been why we've been able to find area as long as it's above the x-axis. So that's why that's been working. So I just want to use these properties just to kind of get you used to them. So let's say that I have, for instance, I want to find the definite integral of f of x from 0 to 5. So I know these things about f of x. So I just want to give you a little practice with working with some of these properties. So I can really just take this part here, so I know the value of this integral, and then I can also take the value of the one from 3 to 5, and that will get me to the value of this particular integral, so I can just sum those values up. So this will be 2 plus 5, so this would equal 7. So I just want to give you a chance to practice some of those. So why don't you pause the video here and try this one, and then hit play when you're ready. So for this one, so I actually am going to have to kind of back into this, right? So I know that the value of this integral plus this integral would equal 9. So instead now I can actually just subtract. So I can take the value from 0 to 5 of g of x dx, and then I can subtract off this value. So I get that this will be 9 minus 4. So the value from 0 to 3 will be 5. Okay, so I have two more for you to try here. Again, just playing around with all those rules. So hopefully you wrote them down. Give these a try, hit play when you're ready. So for this one, so I just flipped the limits of integration. So I already knew this value. So if I just flip the limits of integration, this will equal -5. Now for this one, so we needed to know the value from 0 to 5 of f of x. So just to remind you, we did that earlier here. So the value of this was 7. So I can actually now break this into two pieces. So I can use this integral value plus, I already know this value. So I can just go with these separately. So this will be 7 plus 9. So this is 16. So there's kind of the idea behind that. And then I have just one more thing I want to talk about, so just integrability with continuous functions. So if a function f is continuous over a closed interval, and if f has finitely many jump discontinuities, then the integral exists, and f will be integrable over that closed interval. So I think the best way to understand what this is really trying to get at is another way you can think about this is, when isn't a function integrable? What does that even look like? So I have an example. So when we think about what's actually integrable, so lots of functions are actually going to work for integrability. So even if they are have jump discontinuities, you could still integrate them because you can break them into pieces. So something that would not be integrable, this is kind of like one of the classic examples. So this is a really strange function. So if you just think about what it would look like. So the value of this function is going to be 0 if the number is rational and 1 if the number is irrational. So if I just think about like a couple of values here. So any whole number would be rational, right? So this would be like 1 and 2 and 3 and then like 1/2 and 1.5. There's lots of actual rational numbers here. But anything irrational, so, you know, if you took something like, I don't know, the square root of 2, so that would be irrational. So then I'd have something up here. And so even if you're like right next to the square root of 2, probably next to that you could find another rational number. So what you end up getting is you end up getting like this really crazy looking function that's like very difficult to actually distinguish between. And there are infinitely kind of many jumps kind of going all over the place with this. So this would be a type of function that you can't integrate. So it's pretty crazy stuff that you can't integrate. A lot of things can be integrated. That's maybe where I'll just kind of simplify and leave that. Okay, so that's a whole lot of theory in one video, but hopefully that kind of gives you an idea of the more theoretical aspect of a definite integral and just some of the properties. I have some other videos on this, so hopefully I'll see you in another one.